Hello, this is Algebra Master, and this is episode 3 of Blindly Mathematical. In this episode, I will not be talking about an unsolved problem because I will be explaining some math to get you viewers ready for the next few unsolved problems, because the next few unsolved problems all deal with prime numbers. So I thought it would be important to get you guys up to speed on what prime numbers are. Prime numbers arise from a problem dealing with perfect divisibility. What is perfect divisibility? So imagine you have a whole number of items and you want to divide them among a whole number of people so that each person gets a whole number of items. For example, say you have 60 of a certain item and you want to divide it among 15 people, each person would get exactly 4 items, as opposed to something like dividing 8 items among 3 people. This would not be perfect divisibility or even divisibility or whatever you want to call it, because each person would not get a whole number of items. Someone would have to get a fractional part of an item. For instance, each person would have to get 2 and 2/3 of an item. So, prime numbers arise when you're asking yourself about the factors of a number. What are the factors of a number? They are the numbers that multiply together to give you a number. So for instance, if we look at 60, you have 1 times 60. Those are two factors. 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10, 10 times 6, 12 times 5, 15 times 4, 20 times 3, 30 times 2, and 60 times 1. So if we look at all of those factors and we look at each of them as they only appear once, we double counted quite a few of them. For instance, we counted 3 and 20 and then 20 and 3. That wasn't really necessary because multiplication is commutative, meaning that the order you multiply doesn't matter. 20 times 3 is really the same as 3 times 20. They both equal 60, so it makes no difference one way or the other, the order you multiply things. So with prime numbers are special because their only factors are 1 and themselves. Some of the first prime numbers would be 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 53, 59, 61, 67, 71, 73, and so on. There are an infinite number of prime numbers, and which has been proven using something called the sieve of Eratosthenes, which is an extremely visual method, so I'm not going to bother with that. If you want to learn more about that, there's some other channels that cover that great idea, but it's an extremely visual concept, so that's beyond the scope of this channel. As far as prime numbers go, there are an infinite number of them, and they have some interesting properties with the gaps between them. Namely, we can group together sets of two or more prime numbers, and mathematicians have even named different collections of prime numbers. For instance, if you take two prime numbers and the distance between them, meaning if you take the bigger one minus the smaller one, if the distance is 2, they're called twin primes. For instance, 11 and 13 are twin primes, 17 and 19 are twin primes, 29 and 31 are twin primes, 41 and 43 are twin primes. There are an infinite number of sets of twin primes. What about if they're 4 apart? If they're 4 apart, such as 13 and 17, or 37 and 41, they are called cousin primes. If they're 6 apart, for some reason they're called sexy primes. Evidently, some mathematicians were getting bored out of their skull. They had nothing better to do. But to be fair, that's how some of the best mathematical advances came about. After all, Newton was working on a farm and was bored out of his skull when he came up with calculus, so I mean, I guess boredom can be a good thing. I certainly don't mind it. So, prime numbers come up in a lot of problems, some of which would be the twin prime conjecture, which states that there are an infinite number of twin primes, and your goal more or less is to prove that that statement is true, that there are an infinite number of twin primes. There's the Gold-Bach conjecture, stating that you can add that all even numbers two or greater, I mean, all even numbers four or greater can be written as the sum of two primes. And then, of course, there's the Riemann hypothesis, which is the most complicated of all these problems. It deals with adding up an infinite number of numbers and tells us and reveals information about how the primes are spaced along the real number line. And so far, there's a lot mathematicians don't know about these problems. I myself am still very, very new to these problems, so I mean, you know, they are not going to be easy, and they're quite a bit harder than the first problems that I demonstrated, such as the Collatz conjecture and three cubes problem. These anything whenever you start dealing with primes, I mean there are plenty of solvable problems with primes, but anything dealing with primes tends to be quite a bit more complicated because it usually involves taking a lot of obscure pieces of mathematics and throwing them in a blender. Take modular arithmetic, for instance. Modular arithmetic, some algebra. Um, they usually involve some logarithms, which are a way of rewriting exponentials, basically, which I'll get into later, because those are really important, say, like in prime number theory. Back to the point though, prime numbers are only divisible by 1 in themselves, so 2 is only divisible by 1 and 2. There isn't anything else you can multiply by another whole number to get 2. Um, Same for 3, 5, 7, 11. As for why 1 is not counted as a prime number, because that can only be counted as 1 in itself, that's just because of this thing called the fundamental theorem of arithmetic, which states that all whole numbers can be written as a unique product of primes called a prime factorization. Every number has a prime factorization including primes. For 2, it's just 2. 3, it's 3. For 4, it's 2 times 2. For 5, it's 5. For 6, it's 2 times 3. For 7, it's 7. For 8, it's 2 times 2 times 2. For 9, it's 3 times 3. For 10, it's 2 times 5. For 11, it's 11. For 12, it's 2 times 2 times 3. For 13, it's 13. For 14, it's 2 times 7, and so on. All these various prime factorizations will only appear once on the real number line. One prime factorization for each number. So when I say one prime factorization, I mean the number of times a prime appears in a list in the prime factorization will, so for instance, if you have two twos and a three, or you have three twos and a five, or something like that, those are all unique combinations. Or three threes and a two is different than two twos and a three. But when you start incorporating ones as primes, then anything times 1 is itself. So you could say, for instance, that 2 is 2, but you could also say it's 2 times 1, or 2 times 1 times 1, or 2 times 1 times 1 times 1. And all of a sudden, this rule breaks down. So we figured, okay, we can either ditch this fundamental theorem of arithmetic, which is really useful, or we can just exclude one from the list of primes. The choice was obvious. We had to exclude that one just so we could simplify everything else. And thank gosh mathematicians did, because it really did simplify a lot. It allowed us to keep prime number theory, it allowed us to keep the fundamental theorem of arithmetic, and it allowed us to continue to solve problems like the orchard problem. Another problem I'll talk about in an episode. That's another prime number problem. Well, that's actually more about coprimality, but that does deal with prime numbers. Anyway, this concludes episode 3 of Blindly Mathematical.